All right, students, welcome to your AP acid-base walkthrough question toward the beginning of our Unit 8 acid-base understanding. Again, like usual, we're going to go over conceptual, and then I actually think that I'm not doing any AP FRQ today because the AP FRQs go way too far into the material that we're just not quite there yet. So I'm going to hit up 3 conceptual today. It'll be questions 2, 4, and 5. Sorry for all the scrolling if that made you a little sick. I apologize. So let's go ahead and begin. So question 2 on our workbook, page 1 of Unit 8 workbook, asks us, we have arsenic acid reacts with an equal concentration of sulfate ion. At equilibrium, the concentration of H3 or arsenic is greater than the concentration of HSO4 minus. Write the equation for this reaction and state which acid is the stronger one. So we have 2 acids essentially competing who's going to be the better acid and therefore who will take on the kind of sub role as the base. So what we have here is, according to our equation, we have H3ASO4 arsenic in aqueous solution, because water tends to be the environment that all of these reactions are carried out in. Okay. Reacting with SO4 minus sulfate ion aqueous. Now, we see 2 essentially weak acids, so we know we're going to be in equilibrium. But the question is, which one of these weak acids is the stronger of them? So we know that we get H2. Why is this keep on adding a line? H2ASO4 minus the deprotonation, and we get HSO4, okay, minus. And you're like, well, how did I know that that was going to be my result? Well, in the problem, it tells us that I have these 2 species present. The H3ASO4 is our known reactant, arsenic, but we don't see HSO4 minus as a reactant. In fact, we see sulfate as a reactant. So you know then that in order to have this molecule present, sulfate had to have become that molecule because it has the same base of SO4 minus with an addition of an H proton. So you know then that that is, okay, part of the products. And if you know that's the product, you know that it got that H from somewhere. So you know that arsenic now is down 1 proton. So it has a negative charge. And this, also has a negative charge. And you see that my charge decreased by 1, a proton of H plus for arsenic, and my charge increased by 1 for sulfate to become HSO4 minus. Okay. So based on this reaction, and by the way, all this would also be aqueous. Based on this reaction, which one evidently was the stronger acid? Well, what we see here is that the proton from arsenic got transferred to the sulfate. So the arsenic, okay, acted as the acid. But what we see in the problem, and this is, of course, the conjugate acid, and I'm actually doing this, sorry, this is the conjugate base, and in a different color, this we see that the sulfate acted as the base, and this is the conjugate acid from that base, okay? Now we're told that arsenic's concentration is way greater, or at least significant enough greater to note that than the HSO4 minus. So we know that H3ASO4, okay, is a worse acid. Here's why. It dissociates less, okay? If I have more, I'll color code this all. If I have more, why can't I write this down? O4, then the other potential acid in solution, the conjugate acid, HSO4 minus, that means that this acid is less dissociated. It stays intact, okay? And this acid is less abundant, okay? So what could happen is that this acid could go further, and it can go from HSO4, okay, back to reverse it, right? Back to SO4 2 minus. So we see that this, because of less abundance, we know that the reversible reaction was favored in terms of HSO4 going back to SO4 2 minus and donating its proton to H3ASO4. So that means that which acid is the stronger one? HSO4 is the stronger acid because it's a better acid. Okay, it's a better acid because it ionizes more. So that's kind of your conceptual walkthrough for understanding that problem and also using it as a review of the relationship between conjugate pairs, as well as how we understand dissociation in terms of equilibrium position. Okay, guys, so let's continue on with question number 4 in your workbook, page 2. This is a strong acid, strong base reaction. So here we can assume that we have complete ionization of both our base and our acid. And we're being asked, what is the mass of sodium hydroxide that must be added to 500 milliliters of 0.02 molar HI to obtain a solution with a pH of 2.5. So what you see here is that you see a problem where after mixture, you have an excess of one of your solutions, which is the acidic solution. Because if I have a pH after mixing, I've gone past neutralization, because at neutralization, theoretically, for a strong acid, strong base, it would be a pH of 7. Well, I've gone far past that, and now I have an overall pH of 2.5, which is favoring the acidic, okay, the acidic end of the pH scale. So I know that I have HI excess. So I have excess H3O. So what I can do is I can calculate, well, what is my concentration of excess H3O based on my pH value? So I know that H3O plus excess is going to equal 10 raised to the negative pH. And when I plug that in, it's 10 raised to the negative 2.5, which means I have a molar concentration of 0.00316 molarity. Sorry, I don't know why I'm not even shaking and it's the pen's freaking out. Give me 1 second. 0.0016 molarity. Okay, so that's my concentration of excess H3O, but that doesn't get me directly to my concentration of NaOH, which I can then figure out my grams, my mass of. So now I need to go back to and say, well, I remember that H3O plus excess is also equal conceptually to the amount of, okay, initial condition wise or starting conditions or, yeah. Okay, yeah, we'll leave it at that. Of H3O plus, okay, minus OH concentration. Because obviously to have excess, that means my overall total amount of H3O plus present in solution must be this much greater than my OH minus. Because if they're in a, here we have a 1-to-1 ratio because for every 1 H I have 1 OH minus according to my strong acid, strong base. So what I see then is that like, oh, well, that's the conceptual understanding. And if I can figure out what H3O plus was overall, right, then I can figure out what my OH minus is because I know what my excess has to be. So according to my prompt, I'm told that H3O plus from the prompt is, okay, 0.02 molar. Okay, so that's what I start with. And notice I'm not adding any more HI, I'm adding NaOH. So I know that I can't add more NaOH than my HI. Like I'm going to add less than that somehow. So my total is represented by my initial starting point. Okay, I'm not changing the HI, I'm changing the NaOH. That's what I'm controlling. Okay, so for, by the way, for a titration, we would say then that the titrant, okay, oops, what did I do? Hold on. The titrant for this reaction of between NaOH and HI to produce H2O and NaI. Okay, the titrant is the NaOH. All right. If you were going to put this into lab, that's what you're adding in. So if I know that, then what I can do from my prompt is I can simply plug it in. And what I get then is only one variable is unknown, my OH minus concentration, my total OH minus that is allowable to get the necessary excess H plus concentration. So then what I do is I plug this all in. I say, well, 0.00316 molar is equal to my excess hydronium or H plus concentration is equal to the concentration total of H3O plus that I can have that I start off with, which is 0.02 molar minus some value, okay, OH concentration. And when I solve for this, I get that the OH concentration must be equal to, okay, the max amount of OH I can have in order to get the excess H3O plus in solution, or H plus, is 0.168, or actually 0.0168. Okay, 0.0168 molar. And if I know my molar concentration, I now can use molar mass and the specific volume that it has to be added into to figure out the amount of grams. So I know that 0. So now what's the grams of OH minus? Well, I know that the molarity is 0.0168 moles per liter. I need to get to grams, so I'm going to do some times. Okay, well, I know that I have a liter value. I have to put it into 500 milliliters. So I have to do 500.0 milliliters. Okay, actually, which I can then convert to liters so that I cancel out my units. So it becomes 0.5000 liters, and that cancels out my liters. So I'm left in now value of moles of NaOH, but I need to figure out grams of OH. So I need to get to grams of grams of NaOH. So now I'm going to do times, okay. Let me do a different color. Times, well, what's the molar mass of NaOH? Well, I know for NaOH, the molar mass is about 40 grams of NaOH for every 1 mole of NaOH. And that cancels out my moles, and now I'm left in grams of NaOH. So my gram value, okay, for NaOH is, for a total of, 1 second, let me get my answer. That is equal to 0.34 grams of NaOH were required. And that is my answer. Now, if you're thinking, wait, I just went from concentration of OH minus to using that for my mole concentration of NaOH. Yeah, I can do that because I know that whatever my mole value of OH minus is, NaOH is a 1-to-1 ratio of OH minus that it produces. So that's why I can use my mole value or molarity value that I found for OH minus and say that it also is comparable or equivalent to my molarity value of NaOH required. Because in order to get that many moles of OH minus, I needed a 1-to-1 ratio of NaOH. So that's the end of that problem. And hopefully that made sense. Hopefully that walkthrough and that color coding helped. And then let's move on to number 5, which is really, really short. And it says that calculate the pH of a solution with 1.2345 times 10 to the negative fourth molarity of HCl, a strong acid. Now, remember how I said let the problems teach you, okay? That's a reminder. HCl is a strong acid. Okay, HI, the problem number 4, it also mentioned that this is a strong acid, right? So start collecting those little things in your brain. And if you want to calculate the pH, all you have to do is recognize that, first of all, this is the reaction it's talking about. If it's a strong acid, you know it goes to complete dissociation. So it goes to H plus and Cl minus in water. Okay, H plus and Cl minus. Okay, and so what you have to do is you just have to, 1 second, you just have to use the manipulation that if pH is equal to negative log of the concentration of HCl, of H plus, and HCl is in a 1-to-1 ratio, right? For every 1 mole of HCl, you're going to get 1 mole of H plus. So you know that the starting molarity of HCl is equivalent to the molarity of H plus in solution. So then you can just simply plug in and say this is equal to negative log, okay, of 1.2345 times 10 to the negative fourth molarity, and we don't really have units for pH, and you just get a value of 3.9085 to the proper sig figs of, I started off with 1, 2, 3, 4, 5 sig figs, and I end with 5 sig figs after the decimal. That is a 5 sig fig pH value. Okay, so that's kind of the end of that one. Tomorrow we'll be looking into, or in the next class period, you guys will be looking into equilibrium Ka, Kb with acid base, weak acid base problems, and the calculations that accompany it. So best of luck. Bye, everybody.